June 17th, question number 5. Given triangle MRO shown below with trapezoid PTRO, MR is equal to 9, MP is equal to 2, and PO is equal to 4. What is the length of TR? Okay, in this particular case, we know that PT must be parallel to OR because they're telling us that's a trapezoid and at least one pair of opposite sides in a trapezoid are parallel. So we can also see with that information that we have similar triangles. We could easily prove that angle M is congruent to angle M, reflexive property, and that angle MPT and angle MOR are congruent because of corresponding angles formed by two parallel lines and a transversal. So this is a similar triangle proportion problem. So the most important part of these problems is just to remain consistent in the proportions that you create throughout this whole entire video lesson. Now in this case, they're asking for TR, so I can go directly to TR and put a little X in there. And I can see that they've given me MR, the whole entire side. So a part of remaining consistent is knowing the whole entire other side of the triangle, which would be 2 plus 4, which is 6. And now I can make a very consistent proportion, understanding that because we have parallel sides, we do have side splitter theorem, and parts PO and TR can be used in proportions as long as you remain consistent. So the proportion that I'm going to create is the whole side on the left, 6 over 4, is going to be equal to the whole side MR on the right, which is 9, over the part we're looking for, which is X, because that 4 PO corresponds to TR. So I have a consistent proportion. I'm going to cross multiply and solve. And there's my answer. X is equal to 6. August 17, number 5. In the diagram below, AD intersects BE at C, and AB is parallel to DE. So I'm going to get that into my picture. It's a multiple choice, so I'm going to draw all over this. Those are parallel. If CD is 6.6, CD is 6.6, and DE is 3.4, 3.4, and CE is 4.2, CE 4.2, and BC is 5.25, 5.25. What is the length of AC to the nearest hundredth of a centimeter? Now this once again is a similar triangle proportion problem, but you have to be careful in how you set up the corresponding sides, because remember, corresponding sides of similar triangles are in proportion. So I'm going to kind of set that up at the beginning here. So I know that these two angles are congruent because they're vertical angles, so I'm going to go opposite them, put one slash there and opposite the other one. Those are corresponding sides. Now we also know that because those are parallel, that angle A, I'll put 2 marks here, and angle D are congruent because of alternate interior angles formed by 2 parallel lines and a transversal, which means that their opposite sides are corresponding, which leaves the last side. I'll put 3 notches there and 3 notches there. So once we have all of the notches in and we know the corresponding sides, it's easier to not make a mistake. So what I'm going to do is look for a pair of corresponding sides where I have numbers. I notice that in my smaller triangle I have 4.2 for the two slashes and 5.25 in the larger. So I'm going to put the 4.2, the smaller side, over its corresponding side in the other triangle, 5.25. Remember, there's lots of proportions that will work. I'm trying just to remain consistent. So here I just need to remember that I used corresponding sides and I put the smaller triangle on top. So now I'm going to look for the corresponding side of the smaller with the 3 slashes because the X that I'm looking for is AC. So I'm going to use the 6.6 on top. and my x is going to go on the bottom. So I just remained consistent here. So now I can cross multiply. I'm going to use my calculator to help me, but 4.2 times x is 4.2x. I'm going to need help with this other quick one, so I'm going to clear that out and multiply 6.6 times 5.25, get 34.65. Of course, I'm going to divide by 4.2 on both sides. And on my calculator, I just need to go divide by 4.2, enter, we get 8.25. And there it is. August 17, number 13. In the diagram of triangle ABC below, DE is parallel to AB, and CD is 15. They've put that in there for me. I'm always going to double check. AD is 9. They put that in there for me. And AD is 40. Find the length of DE. Okay, DE is right here. I'll put a little X in there. Now, here you need to be careful because true, we have two parallel lines, triangle inside a triangle, which does tell me that I have similar triangles, right? I can easily prove that as I did before. However, you need to be very careful when you're using the side of AB and the side of DE, which I call inside the triangle. Here, the side splitter theorem does not apply. I can't use 15 and 9 in my proportion, right? I have to be careful to use whole sides of actual triangles. So in order to do that, I'm going to make a quick calculation here and figure out this whole entire side just by adding 9 plus 15, which is 24. Now I could create many proportions that would lead to my answer. So why not do this one? So I'm going to put the 15 over the x. So here I'm doing a proportion like within the triangle. But as long as I do the same corresponding sides on the other one and remain consistent, I should be okay. So if I do the 15 over the x, then I have to do the 24 over the 40. And now I'm going to cross multiply. 24 times x is 24x. And I'm going to multiply 40 times 15, which is going to give me, I believe, 600. Take out the calculator just to show you. 15 times 40. And then divide both sides by 24. And we're going to get x is equal to 25. DE is equal to 25. There it is. Okay, January 18, question number 23. Now, here is a problem which is a little different from the rest. This is a problem that has to do with similar triangles, but it's when you have a right triangle and an altitude drawn and creates two other right triangles within triangles. These are all similar triangles, and we can prove it. However, it's harder to know which sides correspond with which sides, which is why we have the altitude rule and the leg rule, right? So in the diagram below of triangle ABC, ABC is a right angle, AC is 12, AD is equal to 8, and altitude BD is drawn. Find the length of BC. So I'm going to put a little X here in BC. Now, when I refer to the leg or the altitude of this problem, I'm referring to the larger triangle ABC. Is it a leg of triangle ABC or an altitude of triangle ABC? And the thing we're looking for here is a leg of triangle ABC, which is why we're going to use the leg rule. And you might remember that the leg rule says take the leg and put it also down here. Not the other leg, but the same leg, right? These are mean proportion problems, so you're going to multiply it to itself. And the other two parts you're going to remember are the entire hypotenuse of the large triangle and the projection, which is the part that's related to the leg that we're using. Okay, so if I go back to the problem, I can see, well, X is my leg, so I have, I'm gonna redo this proportion, my leg, and I also have the whole entire hypotenuse, which is AC, which is 12. However, you need to be careful. That 8 is actually the projection of this leg. And this part right here, CD, is the projection of the leg we're using. So you do need to make a quick, simple calculation of 12 minus 8 to figure out that CD is 4, and that is the projection of the leg we're looking for. So now we have enough information to begin solving for x. We're going to cross multiply, get x squared is equal to 4 times 12, which is 48. To get rid of a square, we use a square root. X is equal. Now I look at my answers and I can see they're all radicals. They're all irrational, but they're all simplified as well. So you might remember that when we're simplifying a radical, you need to know your perfect square numbers. I usually jot them down until I get to a number that's bigger than the number inside my radical, my radicand. And I also, on my scrap paper, write down the factors of 48, 1 times 48, 2 times 24, 3 times 16. I can kind of stop when I find a square number on the right side of this column, because that's definitely going to be the largest square number that is a factor of 48. So I'm going to divide radical 48 into, I always put the perfect square number on the left, 16 times 3. And the square root of 16 is 4, radical 3. January 18, question number 32. Triangle ABC and triangle ADE are graphed on the set of axes below. Describe a transformation that maps triangle ABC onto triangle ADE. Now, one thing that you could quickly observe when you look at triangle ABC and triangle ADE is that triangle ADE is clearly larger than triangle ABC. So there's only one type of transformation that changes the size of the image, and that is a dilation. So it says describe a transformation that maps ABC onto triangle ADE, and I'm going to write it is a dilation. Furthermore, if I wanted to be even more specific, I could even tell you the scale factor, right? If I wrote a D here. Because if I look at A to B, I can see that to go from A to B, I'm going up 1, 2, 3, 4 across 1. So if I do that one more time, 1, 2, 3, 4 across 1, I get here. That would be a scale factor of 2. And if I do it a third time, 1, 2, 3, 4 across 1, I can see that that is actually a scale factor of 3. So it's actually a D3. Each side of the larger triangle is 3 times the size of the smaller triangle. Explain why this transformation makes triangle ADE similar to triangle ABC. So another thing we should remember about dilations is that dilations preserve angle measure. Therefore, I'll use the dot, dot, dot. Therefore, triangle ABC is similar to triangle ADE because A is congruent to A. because all of the angles in one are congruent to all of the angles in the other. I know usually we just do an AA is congruent to AA because you can basically stop once you've proven that two pairs of angles are congruent, but in this case, we happen to know that all three are, and therefore they are similar. August 17, question number 7. In the diagram below, triangle ACD has points B and E on sides AC and AD respectively, such that BE is parallel to CD. So they put everything else in the picture, but they didn't put the parallel. I was going to put a little arrow here, a little arrow there. AB is equal to 1, BC is equal to 3.5, and AD is equal to 18. What is the length of AE to the nearest 10? Right? They want this little part here. Again, I'll put a little X there. Now, again, the side splitter theorem does apply. However, we really don't have enough information to use the side splitter theorem. So I'm just going to be careful that I'm consistent in the proportions that I create. So if I have 18, which is the whole entire side on the right side of triangle ACD, right? It's the whole AD. I'm going to figure out what the whole entire side here is, which is really easy to do because it's just 3.5 plus 1, which is 4.5. Now it's much easier to make a proportion which is being consistent. For example, I can put 4.5, that whole other side over there, over the side of the smaller, which is 1, is equal to the whole entire side over here, which is 18, over the x I'm looking for. Cross multiply, 4.5x is equal to 18, divide by 4.5, and x will be equal to 4. And there you have it. June 18, question number 4. In the diagram below, AF and BD intersect at C. And AD and PBE are drawn such that the measure of angle D is equal to 65 degrees. The measure of angle CBE is 115 degrees. DC is equal to 7.2, AC is equal to 9.6, and FC is equal to 21.6. What is the length of CB? So we're looking for the length right here of CB. Okay. Well, first of all, we're going to put in some missing numbers so we could see how these triangles are similar, and then furthermore know which sides correspond to which sides. Well, I see they gave this exterior angle of 115 degrees. So if I wanted to figure out what its linear pair is, two angles that are on a line sum to 180. So if I subtract 115 from 180, I get 65. And I can see that I basically have what must be alternate interior angles, which means these must be parallel. And we know that these two angles are congruent because they are vertical angles, right? So we now can figure out what all the corresponding sides are. So opposite my 65-degree angle is this 9.6. Opposite of this 65-degree angle is my 21.6, which means opposite my angle A is going to be my 7.2, and opposite my angle F is going to be the x that I'm looking for. So I can now come up with a proportion that makes sense. So here I'm going to now decide, remember there's many proportions that would work. So if I went to the smaller triangle and I put the 1 over the 2, it would be 9.6 over 7.2. And if I did the same with the other triangle, put the 1 over the 2, the 1 mark is the 21.6, and the 2 mark is my x. And now I'm going to cross multiply. 9.6x is equal to, pull out the calculator, 21.6 times 7.2. I get 155.52. I'm going to divide by 9.6 on both sides. I get x is equal to, divided by 9.6. I get 16.2, and I can see that that's right there, 16.2. Now I am going to move on. June 18, number 11. In the diagram below of right triangle AED, BC is parallel to DE. Which statement is always true? Okay, well, if we looked at these two triangles, right? They both share angle A. So we know that angle A is congruent to angle A, reflexive property. And we know that both of them have right angles. Angle ACB and angle AED have right angles. So just from AA is congruent to AA, we know that these are similar triangles, and therefore similar triangle proportions will be in play. But to make this problem a little bit easier for you to see, sometimes it's helpful just to kind of pull out these two triangles. So I can use a little tool here. This is triangle A, B, C, and then if I use my tool again, I have triangle A, D, E. I can bring this one over here, and I have triangle A, D, E. It's much easier to see which sides correspond when you pull them out. It's a very helpful hint for some of you. So here now I could say that my smallest side corresponds to this smallest side, AC corresponds to AE, and AB corresponds to AD. So now when I come and I see, well, which one is always true? I'm looking for one that has a consistent proportion. So let's look at number 1 first. AC, okay, over BC. So I can see in the small triangle, they're doing the 2 over the 1, which means they have to do the same in the other proportion. So if AC is over BC, here it says DE is over. See, they reversed that. They put the 1 over the 2. So, not good. All right, let's take a look at the second one. Let's erase this. AB over AD. AB over AD puts the 3 of the small triangle, the 3-prong, over AD of the larger one, which means they have to put the small over the large and corresponding sides of the second one. They have to be consistent, which means BC over DE. Oh, I think that looks good. Let's look again. AB, the 3, put it over the corresponding side over AD, and then they went back and they put BC, the 1, over DE, the other. There you go. That's a consistent proportion. June 18, question number 21. In the diagram below of triangle PQR, ST is drawn parallel to PR. Put in the arrow. PS is equal to 2, SQ is equal to 5, and TR is equal to 5. Find the length of QR. Okay, I'm going to do something a little bit different in this one, right? So in this one, yeah, they want to know QR, the whole entire side. However, I'm not going to make that my x because it's much easier in this case to actually make my x QT and use the side splitter theorem and then add it up with the 5 to find my final answer. So the side splitter theorem says when you have a triangle inside a triangle with one parallel side, so these are similar triangles, we can use this side and this part in a proportion to the same corresponding parts on the other side. So I can say that 5 over 2, for example, is equal to the x over 5. Cross multiply. And get x is equal to 12.5. However, you need to be careful here that x wasn't what they're asking me for. But now that I have my 12.5, and I know that this is 5, I can add them up to get QR, which will be 12.5 plus 5, which will be 17.5, which is my ultimate answer. And 17.5 is the same as 17 and a half. June 18, number 23. Line segment CD is the altitude drawn to hypotenuse EF in right triangle ECF. If EC is 10 and EF is 24, then to the nearest tenth ED is. Okay, so often when I see a problem that tells me an altitude is drawn in a right triangle, it usually leads to either a leg rule or altitude rule problem, right? Rules that are meant to help us do pretty complicated similar triangle proportions. So what I'm going to do here is I'm going to draw a right triangle. And usually, not all the time, but sometimes it's more helpful to think of these problems as a right triangle kind of turned upside down. You know, remembering that this is the right angle, and that we're dropping down, and altitude means it's perpendicular, right, to our base, right, meaning that these are also right angles, right? Well, it says line segment CD is drawn to hypotenuse EF. So the hypotenuse has to be down here, right? So here's EF, and if that was a triangle ECF, that means C is up here. And that means that CD would be down here. So now it's easier to draw in these numbers, right? EC is 10. EF, that's E all the way to F, is going to be 24. And what we're looking for here is ED, right part right there. Well, again, I look at my original right triangle, and I ask myself, well, do I have an altitude or do I have a leg that's given to me, or am I looking for one of those two? And I can see that that 10 represents one of the legs of that original triangle. So I'm going to do the leg rule. You remember that's the leg goes up here and down here, right? The whole entire hypotenuse goes up here on the left side. And the projection of the leg that we were using, which is the part right underneath it, which happens to be my x. So now I can cross multiply. 24x is equal to 100. Divide by 24. We get x is equal to 100 divided by 24, which is equal to 4.2.